I built this power station 2 years ago to power my devices both outdoors and indoors. I built this weatherproof portable power station 2 years ago to power my devices both indoors and outdoors, and to see if I can build something that was cheaper or at least comparable to what's on the market today. And today I'm going to show you exactly how I built this thing. My name is Jeff. Welcome to Imagination Tech. A generator is a great thing. It gives you power in places where there isn't any, such as at a campsite or a flying field, or as a backup in case the power goes out. Gas and diesel generators have been around since forever, but they are bulky, noisy, and usually limited in what outputs it can provide. In recent years, there's been a growth in portable power stations that use either a lithium-ion or lithium iron phosphate battery, so there's now a lot of choices out there. As for me, I built this portable generator 2 years ago, and it's not only provided as backup power for work, as a mobile charging station when I'm out flying my drones in the forest or field, and generally used here in the house to lower our electricity bill. It's got a 500 watt continuous 1000 watt peak inverter, so I can power all 3 laptops at once, a refrigerator, and even a washing machine. It also has Type-C Power Delivery 3.0 and Quick Charge 3.0 ports. And the best thing here is the 19.5 volt 10 amp XT60 ports, so I can power my balance charger or most any DC device that can handle that voltage. And I've also built custom adapters so I can also power my laptop directly with DC power. Normally, a laptop charger converts AC power to DC, but to get AC power, I would need to convert my battery DC power to AC first, which is not really that efficient. Well, I don't have to do that anymore because I can just step down my DC power to the required voltage. So why did I choose to build instead of buy? Here are my 3 reasons. First, consumer portable generators by A LOOOOTTT, EcoFlow, Jackery, and others are expensive. The EcoFlow River is $179 but only has a 300 watt output and a 245 watt hour battery, while the River 3 Max has a 572 watt hour battery and a 600 watt output, but it will set you back $418. The A LOOOOTTT AC2A is also around $180 and also has a 300 watt output and a 200 watt hour battery, while on the higher end, they do have one with 1000 watt output and a 768 watt hour battery, but costs about $500. So for less than price of those lower end models, you can almost get 2 times the battery capacity and more output capabilities, and for about $210–220, you have more than 800 watt hour battery capacity. The second reason is that the outputs are limiting. You can get standard AC plug, a cigarette lighter plug, a couple of USB Type A, and maybe a 1 or 2 Type C ports. If you need something else, you can't really customize these things. And third, other DIY generators for sale are just plain ugly. Obviously, there are also cons when going the DIY route. First one obviously is you'll need a bit of elbow grease, a bit of electric know-how to make sure everything will work together, and patience in choosing your parts. If building a bare-bones portable power station isn't already technical enough, the fancy interfaces and mobile apps that are usually available to consumer power stations is out of the question. Although not impossible, it does raise the complexity by a lot. And lastly, at least for the EcoFlow inverters, their X-Boost actually lets you get away with a smaller rated inverter by intelligently downgrading the output voltage. And what this means is you're running your device at a lower voltage, so instead of maybe 220 volts, maybe it'll just output 200 volts, which is kind of gimmicky because that 600 watt device you're powering, that you plugged in, isn't really running at 600 watts anymore. But nonetheless, it'll let you get away with running it in the first place, where a regular inverter's overload protection would have already tripped. Now let's talk about our design considerations and why a lot of advice on building DIY power stations is really bad. So you can categorize a solar system into 3 main subsystems. Energy collection, which is either your solar panels, wind turbines, or even an AC power supply if needed. Energy storage, which is your batteries and your charge controller. And energy output, which is our AC inverter, USB ports, and other uses of the energy that we stored. Most of the time, people give advice on what they think is right. For example, if I said I wanted to power my refrigerator all day and all night, they might give advice on how much solar panel I needed, when really the answer is about energy storage. All those solar panels will do shit when it's night or rainy. Energy collection only determines how slow or how fast you can charge a battery, but ultimately it's the capacity of the battery that will determine what you can power and for how long. Or if I said, I have a 500 amp hour battery, what inverter do I need? Someone would already have a ready answer for that, but the answer may be inaccurate because the question shouldn't be what inverter do I need, but what do you need to power and for how long? Because I could just be powering a water kettle or a microwave, which would need a powerful inverter, but I won't be using it continuously, so it's not drawing that much from my energy storage. Or maybe I need to power that ref earlier, which needs a smaller inverter, but it would be drawing power for far longer, so you'll need to have plenty of battery capacity. In my area where power outages happen occasionally, I might want just a system purely as a backup to power 3 laptops for 8 hours, but I could afford to have it charged over a couple of days, so I could just have a single 200 watt solar panel to save on cost. In summary, these 3 subsystems are interconnected, but they are 3 distinct variables that you will need to adjust individually based on your needs. With that said, here are my design considerations. My target applications are USB Type-C, PD 3.0, QC 3.0, 19.5 volts so I can power a laptop directly, which can also power my balance charger for my drones. I'll just be needing a modest inverter that can provide 500 watt continuous and 1000 watt peak, so I can choose based on what can fit inside my desired case. So this inverter could power everything from a refrigerator, a portable freezer, laptops, 3D printer, etc., even a small washing machine. But heating appliances which draw a lot of power, like a water kettle or microwave, are out. I want to have a 24 volt system because for the same amount of watts you can deliver it with less amps, therefore less heat and smaller wires. Electronically speaking, reducing voltage from 24 volts to something lower is better than having to boost a 12 volt system to a higher voltage because of better efficiency and flexibility. As for the battery capacity, I obviously wanted to maximize what I could fit, which came out to a 7S 13P battery that provided 842 watt hours. Initially, I could only source out enough 2500 mAh cells to build a 7S 7P battery, but even this was still a very respectable 453 watt hours and could last me several hours charging a single laptop, gadgets, and LiPo batteries. The first thing we need to take a look at is the box or the case that we are going to be using for our power station. And I've already mentioned I don't think that using a toolbox really is a good choice aesthetically. A lot of toolboxes do not look good, and the plastic is oftentimes not really great. The lock and the hinges aren't always very built for tough. So this is why I'm going with this. This is an ammo box or an ammo can. There are 2 sizes. This one is, I got the bigger one here on Lazada. It's also available on Shopee and on Amazon. And on Amazon, you can even get something that's bigger, and it has this tool tray up on top. But locally, this is what was available to me, and the medium is it's a pretty good size. If you can see the dimensions here, that's for the small one. The big one has a 300 millimeter length by 165 millimeter width and 175 millimeter depth inside. But it's slightly smaller than that. But you know, this is a good approximation of the size that we are going to be getting. And as mentioned, the plastic on this is really durable. It's really tough. I had a hard time, cutting through it, drilling through it for the holes. But yes, it's really tough. The hinge is really tough as well. It's made of polypropylene plastic. So yeah, as you can see, the hinge here is really made for tough. So you can really, fill this with all of your components, and it's not going to be a problem. So all of the products that I'm going to be mentioning on this video, I'm going to be linking them all down below. Make sure you click on those links if you intend to buy any of the parts that I am showcasing on this video. So the MPPT 7210 comes in this unlabeled box, and it also comes with a manual. Thankfully, it seems to be written in English. It's in an aluminum housing, so it's probably also a heatsink, doubles as a heatsink. It's thicker than expected. I just saw this picture online, but I wasn't expecting it to be thick like this. So I've hooked it up to our power supply, and we're going to give it 18 volts, wrapping up from 0. Let's see when it turns on. It turns on around 8 volts. Let's see if it can go down to 10 volts. So you can see power here drops, and as well as the fan. So let's drop it down to 7 volts. So at 8.5 volts, it turns on again. But at 8 volts, it's still not enough voltage to power on this thing. For the output, I'm going to be using these universal car charger panel outputs. And the nice thing about this is, well, first thing, they're aesthetically pleasing. So, and it has a uniform look. So that's going to be really good, at least on the aesthetic side. They also have these waterproof covers, which are great because you know, even if it rains, I want it to have some, you know, some sort of protection. It's not going to be totally waterproof, but it's going to prevent rain from getting into those ports. So this one is PD 45 watts, and this is for quick charge 3.0. And we also have this this cigarette lighter for different applications, as well as this main switch and this voltage meter. So this takes an input of 12 or 24 volts, but what I've found is that it can take anywhere between those two voltages. So as you can see, it ramped up from 7 volts and now it's at 24 volts. And this one as well, if you flick the switch, oops, you have to turn on by the power supply. So it turns on at around 7 volts, and it can measure voltage anywhere from 12 to 24 volts. Can even go a little bit over 24 volts, but yeah, so once that's powered up, it's going to light up like that. And I chose the color blue because I think it's really nice, but this is available in green and red as well if you prefer those colors. They also have this universal screwing lock mechanism. So you know, you could, as long as they have the same form factor, you could switch them out. I think you can even design one in 3D and 3D print that, but probably won't be as waterproof unless you probably need to design a cover like this as well. This is the inverter that we're going to be using. This is the Pato inverter, and this is, I'm not sure if you can see that, but it's 34 volts for 220 volt outlet, and it supplies up to 1000 watts of AC power. But take note that 1000 watts is the peak and the continuous is 500 watts, which is actually plenty for what I need to use it for. So you have to bear in mind what kind of you know, appliances you want to connect to your inverter. 500 watts gives me plenty for fans, for charging laptops, for even powering up the heater. I think it could even, you know, run the washing machine. So this thing has a fan, and this is where you would hook up your to, you know, your 24 volt in, and then it has a power switch and power and fault LEDs and one AC output and an indicator LED. I was probably going to remove this physical you know, outlet and have something installed on the external side or on the outside of our power generator. So we're feeding it 24 volts via our power supply and turning it on. You can see just how many volts. I'm feeding 24 volts, but probably there's a little bit of voltage difference. So this is the container we're going to be using for our solar generator, and the width is around 7.5 widths of each 18650s. So our series is going to be running this way and our parallel is going to be running this way. Now I was initially planning on doing it like this, where all of the 18650s are lying down and I would have them in series. The length can accommodate 4 of these 18650s, and I was initially planning on doing, you know, a flat pack, 4 at the bottom, and then it's going to go back here on the second layer, 4. But I'm going to be keeping this vertical so that we can have, you know, it's going to run 7 here in series, and it can accommodate around 14 or 15 18650s across the whole length of this container. So this is the battery after it was fully built. It's a 7S13P battery, so it has 91 18650s that are 2500 milliamp hour each, for a total of 842 watt hours. I was only able to fit up to 13P because I also had to leave some space for the BMS and active balancer at the end. We're going to need to fully disassemble our DC output panel so that we can mount it properly on our ammo box. The Spade connectors are a bit tough to get out, but they do come off with enough force, and then you just need to unscrew them all out of the panel. Next up, we'll be cutting our box so we can mount our DC output panel as well as our AC socket. And we'll also be cutting out the space for our PD output and XT60 outlets. To make sure these all align later, I'm going to drill the screw holes and screw the front panel to the case before marking the individual holes and drilling them with a hole saw. For our AC outlet, we also need to mark where our hole needs to be, grab the right size hole saw and cut our hole. We're also going to be cleaning out the burrs using a grinding stone, or you can use a manual file too. I mentioned earlier that I wanted to remove the socket because we are going to use an external socket, but I decided there's an easier and less destructive way of doing this, which is to just solder on some wires to the existing socket. As you can see here, there are just two wires and we're just going to pass them through the already existing holes and solder them to the terminals. And the other end of the wire, we just need to insert our external socket and screw them down. Finally, we can screw our socket to our case. On our inverter, there is a switch here which turns the unit on and off. It's not connected, obviously. But what the switch does, it basically just connects these two wires together and thereby activating the unit. So what we're going to do is we are going to take another switch like this one, and again, a switch just basically connects two terminals with each other, in this case these two. So we are going to be connecting these this switch in between this wire and that terminal, so we don't destroy our inverter. We're just adding another switch in between in series. So you'll need to have both switches on, and this one is going to be the outside of our case. So we can just turn this like master switch inside, leave that on, and then if we turn on this switch from the outside, then it's going to turn on the whole inverter. So this is one wire from the switch, and we are just going to solder it there. I've already removed the original wire, and the other wire we are going to solder onto the original wire that was connected to the original switch. So I recommend using heat shrink tubes, but if you don't have any, electrical tape will do just fine. What's important is that we wrap these bare connections in some insulation so that it doesn't cause any potential short circuits. So we're just heating that up, and by heating that up, it shrinks the tube, hence why it's called a heat shrink tube. So here's our inverter in our box, and it's in the on position. So by itself it won't turn the unit on, but when we flick this other switch as well, then that turns on the inverter. Using a Dremel or a drill with a cutting disc, I also cut a rectangular hole for the switch. While we're cutting things, let's also cut some holes for our XT60 connectors, both output as well as an XT60 input. So this is a 300 watt step down converter which can take anywhere from 6 volts to 40 volts input, and you can adjust the output from 1.2 volts all the way up to 36 volts, and this can put out up to 20 amps. I've set my step down converter to output 19.5 volts so I can power my FPV balance charger, which takes a wide voltage input up to 30 volts. And 19.5 volts is also the voltage of most laptop power supplies, so I can create custom charging cables. You can customize this based on your needs. Let's say if you don't need an XT60, but you need some general purpose 12 volt banana plugs, you can do that as well. And for mounting, I just use some Velcro so I can mount it to the side. That way I can also remove it easily for maintenance. I also got this set of Spade connectors as well as these right angled ones. And this is going to be useful in case you need to add more connectors to the existing wire harness that we have, and that's what I'm going to do. And if you also want to completely replace them, maybe change up to a thicker gauge wire, then this is going to be very useful. So first cut off and expose the end of the wire, and then you just place it here first, and then we're going to crimp the bottom, just the bottom part first. Okay, now that our wire is secure, since our crimping tool is unable to reach this top part, I'm just going to use my long nose pliers, and you can also use pliers in case you don't have a crimping tool. Here I made another one in black, so they come in pairs, and now I just need to pass it through this I don't know, it's a rubbery kind of sheath or cover. So now I just need to connect this to my existing wire harness. Since our DC panel is powered on via this switch, for every device we intend to be powered on with this switch, like this PD charger, we need to daisy chain some wires and spade connectors to be connected to the last spade connector in the wiring harness. For example, this wire, you can see that there's 2 ground wires coming off it. And in my case, I'll be connecting that to my PD charger, which also has some spade connectors, which is daisy chained to this main panel. As for my XT60 outputs, I'll be connecting that directly to my battery. The cigarette lighter that came in our DC output panel doesn't regulate its voltage because I guess they assume you'd only be connecting it to an already regulated 12 volt or 24 volt power source, which isn't good as most of the devices on the market you can buy expect 12 volts and our 7S battery can put out anywhere from 21 volts to 29.4 volts, which is why we need this 12 volt step down regulator. This can put out 12 volts, 5 amps, but you can also source something that puts out 10 amps. What we need to do is take the input wires from our 12 volt regulator, slide them through the spade connector cover, and we can just solder it onto the spade connector. On the output side, we are going to crimp new spade connectors. I removed both the cigarette lighter as well as the voltmeter above it, so we have ample space to work around. And now that we're done with our additional wiring, we can now plug the outputs of the regulator to the cigarette lighter and screw it back. And afterwards, screw in our voltmeter as well and plug the spade connectors in. Lastly, I'm gonna cut a piece of Velcro so I can mount the 12 volt regulator to the side. Finally, let's start putting things inside our case, starting with our battery. So I just wanted to show you this quickly. I showed you this a while ago, but it wasn't yet fully assembled. And I ran out of heat shrink, which is why this is the only section that's been heat shrunk. Not really heat shrunk, I just taped it together. This thing is, it has a backing just to make the bottom a little bit more secure. So, it's one solid piece and there's less risk of things tearing out. It's also been secured with a lot of Kapton tape. Our BMS is over here as well as our active balancer, just to keep all of the parallel cells happy. You can notice that I have an XT30 plug here, which is what I use for charging the battery, and an XT60 plug, which is the output, but they're both connected to the battery terminals. And my thinking is that I don't really need that high of a current when I'm charging the battery, but I need a little bit more when I'm drawing from the battery. Because of all of our output devices mounted up front, I need to insert the battery sideways, making sure that my XT30 and XT60 plugs don't get caught under the battery. We obviously don't want any metal to be touching our battery for safety, so I designed this battery separator that we can place on top of the battery as sort of an insulator. This is also what I used as the backing under the battery. With this on top of the battery, I can safely place my inverter, which is housed in a metal case, above it. I initially made this 2mm thick, but scaled it down in the slicer to 1mm to print faster, and it also just works just as well. These are printed as halves, so you're gonna need 2 of them. Now that we have them printed, we just place each half on top of the battery. I put holes in the design not just for ventilation or to save on material, but also so I can pass my XT30 and XT60 plugs through them as well. In order to keep our wirings tidy, we're going to use these quick connect terminals. So what this does is all of the blues are connected and all of the reds are connected. Let's say this one is coming from battery and you want it to go out to different outputs, then you could connect all of your outputs here and your battery here. How you use this is you just open these up. You take your wire, which is stripped to around 2 or 3 millimeters, just put it in, and you can use from 12 gauge to 28 gauge, and then just snap that back, and that's nice and secure. Here I have one of my quick connect terminals connected to an XT60 connector, which plugs into the battery. And we plug in the wires of our DC output panel as well as our XT60 outputs. Not sure if you noticed it, but our DC output panel has an inline fuse for added safety. The wire for our inverter also has an inline fuse, but uses a blade fuse instead of a glass fuse. Our 1000 watt inverter fits right in behind our DC output devices, and it's a snug fit. So we screw down the positive wire to the inverter and then snap it locked to the quick connect terminal, and then we just do the same for the ground wire. Finally, we get our MPPT charge controller and place it on top of our inverter, and connect the battery wire to the XT30 plug of our battery. Most solar panels have an MC4 connector, so I made my own MC4 to XT60 adapter, and my XT60 input port is connected to the input port of the MPPT, and the MPPT in turn charges my battery. All that's left is to tidy up our wires a little bit and we're done. Well, there you have it. That's how I built my portable power station 2 years ago, and hopefully you'll also get to build your own with the help of this video. Some of the clips in this video go all the way back, while some are relatively recent because a lot has changed in those 2 years. I've had to swap out some parts, and at one point I had literally every output going through this switch, and I eventually learned the hard way why that wasn't such a great idea. So while the finished build seemed quite straightforward, building this thing as well as making this video was hardly a straight path. There are also definitely some things I would like to improve on in the future. While it is a very functional and purpose-built power station, something that looks like it could be used by the military, I would like to have some high-tech 21st century polish by way of some nice fancy displays. Right now I only have a voltage display outside and I have to turn on the output panel. Or if I wanted to know information about charging, I'd have to open it up and take a peek inside at the MPPT. So maybe I could put an Arduino or an ESP32 to get some readings or log data that I can check through a phone app. Speaking of opening, a trade-off I had to make when I decided to maintain the waterproofing of this case is the limited ventilation. When charging and when an inverter is putting out its maximum wattage, it gets really hot inside, and while the individual components have cooling, I have to leave the case open for the hot air to escape. So, like that. The best part is a lot of this is upgradable. I actually have a better PD charger that can put out 45 watts per channel on the way, and for a total of 90 watts. And I will link to that as well, but as I've not tried it myself, try it at your own risk. Other than that, both the battery capacity and the output capabilities of this thing are a winner, and you just can't beat that price. Well, I hope this video has been useful, educational, or entertaining. Do bookmark or add this to one of your playlists. Make sure you're subscribed and click on that bell button and the like button as well so more people get to see this video. And I'm going to leave you with that. As always, keep building and keep flying. Cheers.